Okay, so hello everyone again. This is the lecture number 5 on units and measurements. Today we will go on with the further discussions on significant figures and then we can move on to dimensional analysis. So this may be the last lecture on units and measurement. Let's look up and view the further discussions. Okay, so I'm Sanjeev Lawankar. Let's begin our discussion. Okay, so the course outline for you right now we are on the seventh topic, that is the significant figures, and these all things have been completed in detail. So basically introduction, then SI unit, why was there a need for SI unit, measurement of length, in which we understood two types. One was for very large distances called as parallax method, and second was based upon your for very small distances, which was there was no such certain method, but for an example of oleic acid was given to you. So basically using a very tunneling microscopy in recent times use a tunneling microscopy for the measurement of very small distances. Then measurement of mass, we understood measurement of mass. Then we also understood measurement of time. Finally, in this, we understood the concepts such as relative error, absolute error, percentage error, etc. Also, combination of errors are also being understood, as in what will be the uncertainty if we add two quantities to uncertain quantities, divide those, multiply those, difference to the difference of them, etc. Last class, we were on the significant figures. Let's continue our discussion on significant figures only, and then we can move forward. Fine. So significant figures has to be understood. So these all things are finally understood. I also explained you all the rules which are necessary. I would really suggest you so try to solve questions regarding significant figures, because more and more practice of significant figures will lead to greater clarity of what this basic concept is. Okay. Fine. So these all things are already being done. Let's move on with today. The new concept, that is rounding off the uncertain digits. Okay, so how do we round off? Okay, so simple three rules are there. Just try to understand very easy rules and then we can move forward. Okay. So let me first iterate. So the result of computation with approximate numbers which contain more than one uncertain digit should be rounded off. The rules for rounding of numbers to the appropriate significant figures are obvious in most cases. So obvious as in the our small classes also we have understood some concept. Let's say the number is between 1 to 5, then and not including 5. So we decrease the number, right? So we decrease the number, and if it is 5 or greater than 5, let's say it's still 10, then we increase the number. So this was the basic terminology. Now let us just keep on accepting these rules and let us see what happens. Okay. So this thing has been explained. Let's move on. So a number 2.746 rounded off to three significant figures is 2.75. See, so it's quite evident. It's 2.746, right? So when we round out three significant figures, this is having four significant figures, as you can see. So if you are rounding off it to three significant figures, then it will be 3.7, as it's 4, 6, and because this is greater than 5, so we can directly write this to be 5. Okay, so this has been rounded out to three significant digits. Fine. While the number 2.743 would be 2.74. Why? Because the last uncertain digit is less than 5. So this thing is explained. Moving on, a number by convention is that, the rule by convention is that the preceding digit is raised by 1. The preceding digit, as you can see, the preceding digit is raised by 1 if the insignificant digit is to be dropped is more than 5. So if the insignificant, so this is basically your 6 is the insignificant digit here. If that insignificant digit has to be dropped, then the first uncertain digit, if the preceding digit to it is greater than 5, so what do? We just try to increase that preceding digit by 1. Okay. So if the insignificant digit is more than 5, then what we do? We increase it by 1, and it is left unchanged if the latter is less than 5. Simple thing. So rounding numbers we have already understood, studied in small classes also. So there is nothing to be understood it much more depth here. Let's move on. But what if the number is 2.745? But what if the number is 2.745 in which the insignificant digit is 5? Here the convention is that if the preceding number is even, okay, if the preceding digit is even, then the insignificant digit is simply dropped, and if it is odd, the preceding digit is raised by 1. Okay, simple thing. We will go with an example also for this, for understanding this rule. This may be a new rule, but very easy to understand. Just remember this rule and it will be okay. So then the number 2.745 rounded off to three significant digits become 2.74. Why it becomes 2.74? As you can see, 2.745. This is having how many significant digits? It is having four significant digits. Let us say we want to round it off to three significant digits. Okay. So as the final digit is 5 here, so we must look that either the digit preceding it is odd or even. As it is even, the rule states that if the number is even, then the insignificant digit is simply dropped. If it is simply dropped, then that means we are just writing it 2.74. Let us say this would have been 3, then what would have been done? Then if it is odd, so then the preceding digit is by 1. Then the answer would have been 2.74 again. Okay, so that is just coincidence. Let us say this is not even 3, let us say this is 5 here, then the answer would have been 2.76. Okay, so that were two rules to be explained here. So this thing is done. Next, let's move on. So these are the basic rules. Let's move on then. In any involved or complex multi-step calculation, you should retain in intermediate steps one digit more than the significant digits and round off to proper significant figures at the end of the calculation. So as the name it suggests that you should always leave only and only one digit for more than significant digits and round off the proper significant figures. Okay, so you need to round off. So every time if the answer is, let's say, till 7 or 11 decimal, then generally it's should be in 2 to 3 significant figures only. Now it depends upon the question. Okay, so that line is just based upon the questions. When you do the questions, you will understand this much more clear. Similarly, a number known to be within many significant figures, such as, let us say, so now this number is known to many significant figures, right? You can understand how many significant figures are here. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. So here 9 significant figures involved. Okay. For the speed of light in vacuum is rounded off to approximately 3 into 10 to the power 8 meter per second. Okay, so how that approximately, let us say we have only significant figures up to 1 decimal digit, and what we will do, we will see the first uncertain digit as it is 9 here, so we will directly increase it by 1. Okay, which is often employed in computations. Finally, remember that the exact numbers that appear in formulas like t is equal to 2.0 del by g have large number of insignificant figures. This was also been explained as one of the point in the last class also, that exact numbers or two numbers have infinite number of significant figures. So they can be molded as per our choice or as per our convenience. Okay. Final concluding line of the slide. The value of pi, that is 3.1415926, is known to a large number of significant figures. You may take the value as 3.142 or 3.14 for pi with the limited number of significant figures as required in specific cases. Okay, so as it is an irrational number, the number can even go on. Okay, so it can go on to many large numbers, but we need to stop it according to our significant figures choice or according to our convenience. Okay, so here also the convenience is based upon the calculation involved, and here also the convenience is based on calculation involved. Only difference is that this is having infinite number, this is also having almost equal to infinite, but we don't take it as infinite. We have to reduce it to some of the 3 or 4 significant figure values. Okay, fine, then let's move on. Let's move on with one of the example. Please understand the example very clearly, and then it will be very easy to move forward. Okay, so the each side of a cube is measured to be 7.203 meter. Okay, so 7.230 meter size. Let us say I write a is equal to nothing but 7.203 meters. Okay, let us keep on understanding everything. So how many significant figures are here? Here 4 number of significant figures are here. Okay, this 0 will also be utilized as a significant figure. Why? Because it is inside or it is between two non-zero digits. Okay. Okay, so what are the total surface area and volume of the cube to appropriate significant figures? What does it mean by here appropriate significant figures? What is the maximum value or the maximum significant figures we know for a cube? If it is greater than, if it is 4, then the maximum value which a surface area or a volume can be known is also till 4 significant digits only. That is the main crux. Like let us see the calculation, we will understand much more clearly. So the number of significant figures in the measured length is 4, quite evident as it is 4 here. The calculated area and the volume should therefore be rounded off to 4 significant figures. Okay, so surface area of the cube, we know the formula, that is 6a square. Volume of the cube is basically a cube, we know the formula. So now if you just put these things in the calculator or even try to multiply it using normal multiplications, you will get the answer as equal to 311.299254. Okay, but we cannot give it with certain that the answer is this only. We have to always put it into about of significant figures which are available for the cube. Okay, hence as only 4 significant digits are allowed, therefore as it is 29 here, so as this number is 9 which is greater than 5, hence we will directly upgrade 2 to plus 1 which will give you 3, hence this will be 311.3. Similarly, for this case also 373.714. Again, only 4 significant digits are involved here. Therefore, we will write 373.71 as it is 71 here. So therefore, it is less than 5. Therefore, 7 will be again 71. Okay. So that is the thing we involved here, and hence the answer is 311.3 meter square and 373.7 meter cube. Okay. Let's move on then. Again, new example. So example states that 5.74 grams of substance occupies 1.2 centimeter cube. Okay, so the mass has a significant digits as 3 and volume has significant digits as 2. Okay, so what is the minimum significant digits we have? If the minimum significant digits we have is only 2, therefore the answer, anything which is required after calculation after this things written here should be always with the minimum significant digits, and the answer should be reported with 2 significant digits only. Okay, let's move on. What is written? So express its density by keeping the significant figures in view. Okay, let's look over to the solution. The solution states that there are 3 significant figures in the measured mass, whereas there are only 2 significant figures in the measured value. Quite evident, as you can see, 3 significant figures here, 2 are being kept here. Okay, so hence the density should be expressed to only 2 significant figures. Fine. Therefore, this is a simple calculation. You know what is density? Density is nothing but mass by volume. Mass is given to you, volume is given to you. That try to calculate it, and finally give the answer is only in terms of what we can say 2 significant figures only. Let us say the answer would have come 4.733. Then you would have changed it to 4.7. Okay, let us say if an example, I'm just taking an example. Let us say the example is the density came out to be 4.733. Then you need to change it to 2 significant figures. So just taking the first 3 into consideration as it is less than 5. Therefore, 4.733 would change into 4.7 gram per centimeter cube. Okay, so those were 2 of the examples on your rounding off. Let's move on with the new rules. Okay, new concept now under significant figures only, that is the rules for determining the uncertainty in the result of arithmetic calculations. Okay, so basically what will happen when we are trying to find out let us say we have the length, we have the breadth, we need to find out the value of area, then what happens in those terms, we will understand that. Okay, so let us start with this concept. So the rules for determining the uncertainty or error in the number or measured quantity in arithmetic operations can be understood from the following example. Okay, so let's look at the example once. So the length and the breadth of a thin rectangular sheet are measured using a meter scale as 16.2 centimeter and 10.1 centimeter respectively. There are 3 significant figures in each measurement. Quite evident, as you can see, it is also having 3 significant figures and this is also having 3 significant figures. Okay, it means that the length L may be written as, okay, so why there is a tolerance of 0.1? You may say because the resolution of the meter scale is 0.1 centimeter, or we can say the least count of a meter scale is 0.1 centimeter. Okay, so the smallest thing which we can measure is 1 mm here, therefore the resolution is 0.1 centimeter. So just writing that concept here, we will finally get L is equal to 16.2 plus minus 0.1 centimeter. Okay, what does this line show? 0.6 centimeter. So they are just finding out the value as 0.1 upon 16.2 into 100. When you will try to calculate it, you will get the answer as equal to your 0.6%. Okay. Similarly, the breadth we can return as 10.1 plus minus 0.1 centimeters. Therefore, B is nothing but equal to 10.1 centimeter plus minus 1%. Okay, so I think this can be calculated also. So it's nothing but 0.1 upon 10.1 into 100. Just try to calculate it. You will get the answer as equal to your 1%. Okay. So approx, I guess 1.000 would have occurred, but because we need to find out as one significant digit only, therefore we are finding it as equal to the least one as one significant digit. Therefore, we are finding the answer as 1% only. Okay. Fine. So this thing is explained. This thing is explained. Moving on. Then the error of the product of two or more experimental values using the combination of errors rule would be what? Okay. So what we are doing this will be L into B, right? So L into B will be nothing but equal to the 16.2 would be multiplied directly with 10.1. But how to add the errors here? So basically we have the concept that is delta A by A. So basically delta Z by Z is equal to delta A by A plus delta B by B. And let us say I write it in percentage forms, and this will be percentage, this will be Hello?
Hello.
Yes, sir.
हाँ अंकित, हेलो हेलो, आवाज आ रही है?
हेलो हेलो।
हाँ समीर।
हाँ सर।
मैं ये कह रहा हूँ कि आपका जो ये स्क्रीन है, आपने जो स्लाइड्स बनाई हुई है ना,
हाँ,
की क्वालिटी जो है वो उतनी अच्छी नहीं है, राइट? पिक्सल्स जो है वो बहुत ज्यादा मतलब फट रहे हैं, ब्लर हो रहा है। ये इमेजेस हैं या फिर
इमेजेस है, नॉर्मल इमेजेस है सर।
ओके ओके, अभी ठीक है, अभी ठीक है। ओके ठीक है, आप कंटिन्यू कर सकते हो।
Okay, sir. Fine. So percentage error is basically delta Z by Z into 100. So we can write it for a total uncertainty is equal to delta A by A plus delta B by B into 100. Okay. So as you already know that this is given, delta A by A into 100 is given to you as 0.6% and delta B by B is given to you as 1%. Okay. So we can directly add up, or other, let us you don't have the percentage error, then we need to find it out. So it's 0.1 upon 16.2 into 100 plus 0.1 upon 10.1 into 100. As it is already given, we will directly use the result. Okay, so that thing been explained again. So we have this answer as nothing but equal to, so this is basically L multiplied by B. Okay, that is 163.62 centimeter square plus 1.6%. Okay. Also in the same terms, you can also find the value as 2.6 centimeter. How we will get 2.6 centimeter? So that is nothing but L into B into delta L by L plus delta B by B. So when you will try to find it out, you will get the answer is nothing but 2.6 centimeter squared. Okay. So that thing is also explained. This leads us to quote the final result as. Now basic concept is, now everything which we have learned from the significant figures, rounding, error, etc. has to be utilized here. Okay. So as you can see, first of all, let us see this line. So how many significant figures we had? We had only 3 significant figures. Okay. 3 significant figures for measurement. Please remember, 3 significant figures are for measurement. For the least count, it's only one. Only one significant figure is there. Okay, 0 is not a significant figure, only 1 is a significant figure. That's why for the main base quantity, what we did, we used 3 significant figures. For the error or the tolerance quantity, we used only 1 significant. And that is how the final result, whenever you need to quote, any question comes from the units and measurement concept, always try to understand what are the significant figures for the base number and what are the significant figures for the, what we can say, rounding of number. So here 3 centimeter square is the uncertainty or error in the estimation of area of a rectangular sheet. Now what is the second rule? The second rule is, if a set of experimental data is specified to n significant figures, a result obtained by combining the data will also be valid to n significant figures. Okay. Let us try to understand what this line says. However, if data are subtracted, the number of significant figures can be reduced. Okay, so what they are just saying that if we have set of experimental data and it is having n significant figures, n can be anything, 1, 2, 3, 4, 5, 6, 7, 8. A result obtained by combining the data will also be valid to n significant figures only. So that's the thing. One of the typical example which just previously is an example of this. However, now where there is a turn is in example of subtraction. So what happens in subtraction is that the number of significant figures can be reduced. Let us say, for example, 12.9 minus 7.06 gram has to be done. So both specified is up to 3 significant figures. cannot properly be evaluated as 5.84 grams, but only as 5.8 grams. What is the reason here? The reason is this, because please understand this very, very carefully. It's 12.9 and it's 7.06. It is quite evident that both are having significant figures as 3 only. But you don't know the number here is uncertain, right? It can be 9 also, it can be 9 also, right? So we don't know the uncertain, we don't know the certain value of the quantity which will come at the second point after decimal place. Therefore, what we do is we only give the answer as first decimal place only. Okay, some of the concepts are intuitive, some of the concepts are basically you need to follow the rules. But that's why I'm saying that if you keep practicing this will be very, very clear. Okay. So for example, 12.9 grams minus 7.06 grams, both specified to three significant figures, cannot properly be evaluated as 5.84 grams, but only as 5.8 grams. As uncertainties in the subtraction or addition combine in a different fashion. Okay, so I explained you why it is happening in subtraction. Smallest number of decimal places rather than the number of significant figures in any number of in any of the numbers added or subtracted. Okay, so that was the second rule. Moving on to the third rule, the relative error of a value of number specified to significant figures depend not only on n but also on the number itself. Okay, example is given here. You will understand much more clearly using example. The example states that, for example, the accuracy in measurement of mass is this. Okay, so this is the base value and this is a tolerance value given to you. Whereas another measurement, 9.89 gram, is also accurate to plus minus 0.01 grams. Then what is the relative error? The relative error in 1.02 gram is plus minus 0.01 by 1.02. Quite evident. Simple delta A upon A into 100. But similarly, the relative error in 9.89 would be what? As you can see, quite evident that the relative error in both these scenarios are different. So they are saying that the accuracy may refer, means relative error which is specified for a significant figure depends not only on n. N is basically the number of significant figures, as you can see, but it also depends upon the number itself. So basically, as the number is varying, it was 1.02 in the beginning, it was 9.89 in the second experiment. Then it may differ with the relative error may differ with significant figures also, and it may differ with the number also. Okay. Finally, remember that the intermediate results in a multi-step computation should be calculated to one or more significant figures in every measurement, then the number of digits in the least precise measurement. These should be justified by the data, and then the arithmetic operation may be carried out, otherwise rounding errors can build up. Okay, so the final tool just explains to you that sometimes you need to understand this intuitively, sometimes you need to write everything and understand. Okay, so one of the method which I generally adopt is I try to understand that if there is an uncertain digit happening, what will happen if I put there 9 or if I put 1. If there's a very high variation in the answer obtained, then we need to generally omit that point of decimal place, or let's say omit that significant figure that is not considered significant figure. So just keep on practicing and keep on understanding these rules, and you will be able to solve the problems regarding this. Okay, so for example, the reciprocal of 9.58 calculated to the same number of significant figures is 0.104, but the reciprocal of 1.104 calculated to 3 significant figure is 9.62. Okay, so it's very evident because sometimes reciprocal also happens. So if the question is being asked, find the reciprocal of 9.58, your answer would be 0.104 only. But you cannot ask a question that if I try to do the reciprocal of this, why I'm getting 9.62. You know the reason behind this, because there is an uncertainty happening when you're trying to find out the reciprocal. Okay, so you know the back engineering of it, but what is actually happening is that there will be change in the answer, or there will be some variation in the answer. Okay. However, if we have written 1 upon 9.58 is equal to 0.1044 and then taken the reciprocal to 3 significant figures, we would have retrieved the original value as 9.5. I think the example is quite clear as to understanding why there is a difference in the answer. This example justifies the idea to retain one more extra digit than the number of digits in the least precise measurement in intermediate steps of the complex multi-step calculation in order to avoid additional errors in the process of rounding of the numbers. So what they are trying to say, let us say we have a complete set of solution to be made in which there are let's say 3 to 4 steps, right? This is step 1, step 2, step 3, step 4, step 5, step 6, right? Everything requires calculation. So they're just saying in this 2 to 5 intermediate steps, try not to do significant figures calculation. Try to find out the answer up to all the decimal places. Finally, when you're trying to retrieve the answer at the final step, try to use the significant figures concept only at the last stage to avoid any rounding of errors or any major mistakes. Okay, because sometimes 9.5 to 9.62 can make a huge difference if you're trying to find out something very peculiar. Okay, so that was the basic concept which was involved here, and that leads us to the end of the significant figures. Okay, so let's move to the next concept, that is dimensions of the physical quantities. Okay, so what are these dimensions of physical quantities? So the nature of a physical quantity is described by its dimensions. Okay, all the physical quantities represented by derived units. Please remember what are derived units. So there were basically two units. One were your fundamental units and one were your derived units, right? Derived unit, fundamental units were basically the base units, and the derived units are basically made using base units. Okay, so all the physical quantities represented by derived units can be expressed in terms of some combination of 7 fundamental or basic quantities. Uh, Please remember those 7 basic quantities. What were those? Those were mass, time, current, temperature, candela, that is luminous intensity, and the amount of substance. Okay. So we shall call these basic quantities as the 7 dimensions of the physical world, which are denoted by square brackets. Okay, so please keep on remembering this. These are very, very small few rules which you need to understand. Thus, length is a dimension L, mass M, time T, electric current A, temperature K, luminous intensity CD, and amount of substance mole. The dimensions of a physical quantity are the powers or exponents to which the base quantities are raised to represent the quantity. For example, we know that area is nothing but equal to meter squared, something in meter squared. This is nothing but L squared. That is how we are putting the dimensions. Okay, so this is the basic concept of dimension. Okay, so where we were, yes. So note that using the square brackets, round a quantity means that we are dealing with the dimensions of the quantity. Okay, so we are understanding of the dimensions of the quantity. In mechanics, all the physical quantities can be written in terms of the dimensions, that is L, M, and T. Okay. For example, the volume occupied by an object is expressed as the product of length, breadth, and height. Quite evident, we know. So what is volume? Volume is nothing but L into B into H. We know that everything has a dimension of L only, so we can just write it as L. If you need to find out the dimension of L, okay. If you find a dimension of V, this will be nothing but L multiplied by L multiplied by L, which will give you the answer as equal to LQ. Okay. So that was the example. As the volume is independent of mass and time, it is said to possess zero dimension in mass. So it's M0. We can even write it as equal to M0 here only. And similarly, T0. Okay, because T is having power 0, anything with the power 0 will also always give you the answer as. Similarly, what is force? Let us try to do the force. Let us not to get the result. Let us try to find out the value of force. We know what is force. Force is nothing but equal to mass into acceleration. Okay. You know for mass it's kg. So, okay, let's not write that first. Let's write first this only. So it's kg into what is for acceleration. Acceleration is basically length upon square of time. Okay. So let me write it's meter per second squared. Okay, so if I write for LMT, so then what will be for length will be, as you can see, it is power 1. Mass will be power 1, length will be also power 1, but time will be -2. Therefore, the dimension for your force would be L1 M1 T -2. Okay, that was the basic crux or basic concept regarding dimensions of physical quantities. Okay. So similarly, force as the product of mass and acceleration can be expressed as force is equal to mass into acceleration. Just everything which I wrote is written here, which is equal to length upon mass into length upon time squared. The dimensions of force are, as it is written, mass into L upon T squared, which can be written as M L T -2. Okay. Thus, the force has 1 dimension in mass, 1 dimension in length, and 2 dimensions in time. Okay. The dimension in all other base quantities are 0. Okay, all the base quantities, as in there is no use of current, there is no use of temperature, candela, mole. So if you need to generalize it, you can also write CD to the power 0, K to the power 0, etc. in there. But that is generally not required. Generally, when you will try to solve questions, and even in higher classes also, you will understand that everything is generally being considered LMT. If things arises, some base quantity of, let's say, current arises, then you can use those terms also. Okay. So fine. So this thing is also explained. And dimensions in all of the base quantities are 0. Note that in this type of representation, the magnitudes are not considered. Very evident. If let's say force is having 5 newtons value, then it's not 5 multiplied by L1 M1 T1. We are only and only considered about dimensions of physical quantities. Anything which is in the is in square brackets, then that is in the dimensions only. So note that in this type of representation, the magnitudes are not considered. It is the quality of the type of the physical quantity that enters. Okay, so it is the quality of the type of the physical quantity that enters. There's a quality we are understanding. What is the quality of it? So does it depend upon mass? Does it depend upon length? Does it depend upon time, etc. Thus, a change in the velocity, initial velocity, average velocity, final velocity, and speed are all equivalent in this context. Since all these quantities can be expressed as length upon time, the dimensions are L by T or L T inverse. Okay, so these all concepts written: change in velocity, the initial velocity, average velocity, final velocity, speed. These all concepts will be understood in much more detail when we will understand the next chapter, that is motion in a straight line. Okay, so just relax for a bit and you can understand these all concepts very clearly in the next chapter. Let's move on for now. So since all these quantities can be expressed as length upon time, the dimensions are L by T or basically LT inverse. Fine. So let's now understand dimensional formula and dimensional equations. Okay. So the expression which shows how and which of the base quantities represent the dimensions of a physical quantity is called the dimensional formula of the given physical quantity. Okay. Everything which is written here will be explained in subsequent points. Let us see first the example. For example, the dimensional formula for the volume would be what? Why it's M0, L3, T0? We know it's meter cube. Meter cube means meter has a unit of has a unit of length. So we'll just write L3 because all the base quantities are having 0. So we'll write as M0, L3, T0. Okay, so it's MLT. Generally, it is out as MLT. Even if you change the values LTM or something like it won't differ, but general configuration say that you should write it as MLT. Okay. So for example, dimensional formula for this thing is basically called as a dimensional formula. Okay. So for example, dimensional formula of the volume is M0 L3 T0. And that of the speed or velocity is how it's LT inverse. We know it's meter per second. So meter will give you length. T inverse will give you per second. Okay. Similarly, M0 L1 T minus 2 is for acceleration. Why? Because it is nothing but meter per second squared. So it's L1 and T minus 2 is the dimensional formula of acceleration. And similarly for density, we know for density is what? It is mass by volume. So mass by volume is basically it's M1 and it's L minus 3. So as you can see, it's M1, L minus 3 and T would be 0. Okay. Next thing is, so an equation obtained by equating a physical quantity with its dimensional formula is called a dimensional equation of the physical quantity. So that is the basic definition of what is a dimensional equation. Okay, let me reiterate. So an equation obtained by equating a physical quantity with its dimensional formula is called the dimensional equation of the physical quantity. The examples are put forward in the next lines only. Thus, the dimensional equations are the equations which represent the dimensions of a physical quantity in terms of the base quantities. Okay, there are no use of the values or magnitudes of those quantities or values, and there is no use of any derived quantities only. We are only using base quantities here for our reference. Okay. For example, the dimensional equations of volume V, speed V, force F and mass density rho can be expressed as this. So as I explained in previous also, we can write this also in brackets. So this is for our reference that we are finding out the dimensions of the RHS. Okay, so the dimensions of LHS is basically given on the right hand side with a square bracket again in terms of MLT. Generally, majority of the concepts you will study in future classes will be based upon dimensions of MLT only. Okay. A dimensional equation can be obtained from the equation representing the relations between the physical quantities. Okay, so they can be obtained by representing the relation between the physical quantities, just as we explained here. Okay, now let us move on to dimensional analysis and its application. Okay, I think that is the last concept which we need to understand, and then we'll move on to some of the examples, and that would be the end of this complete discussion. Okay, so let us understand this concept very clearly. Dimensional analysis and its applications. Okay, so the recognition of concepts or dimensions which guide the description of physical behavior is of basic importance, as only those physical quantities can be added or subtracted which are the same dimension. Quite evident. Example, we cannot add a velocity to an acceleration. Velocity plus acceleration added up has no usage, and even it cannot be added. First of all, though, it cannot be added. Okay, so it's an example of the thing which is written here. A thorough understanding, only velocity can be added to velocity and acceleration can be added to acceleration. A thorough understanding of dimensional analysis helps us in deducing certain relations among different physical quantities and checking the derivation, accuracy, and dimensional consistency. What is this dimensional consistency and homogeneity will be explained of various mathematical operations. Okay, so basically, what does it say? That dimensional consistency, as in everything which is written on the LHS, should also be equal to RHS. Okay, so that is how we say that the dimensions are consistent on the left hand side and right hand side. Okay. When magnitudes of two or more physical quantities are multiplied, their units should be treated in the same manner as ordinary algebraic symbols. Okay, so simple multiplications or simple things have to be used. It's quite the thing is that statement is quite evident directly. When magnitudes of two or more physical quantities are multiplied, the unit should be treated in the same manner as ordinary algebraic symbols. We can cancel identical units in the numerator and denominator. The same is true for dimensions of a physical quantity. Everything which is written here, I will try to put examples in front of you also, so that can be easy to understand. Similarly, physical quantities represented by symbols on both sides of a mathematical equation must have the same dimension. So that is one of the crux of your dimensional consistency. Okay. So whatever is written on the left hand side should be also equal to right hand side. The dimensions of both should be same. Okay. Let us say if I use an equation, let's say I use power is equal to force into velocity. Okay, so whatever is written here, when you will try to find the dimensions of this thing, that will be equal to dimension of the left hand side. So this is basically power, and power is nothing but force into velocity. Okay, let's move on. So checking the dimensional consistency of equations. So how we check the dimensional consistency of equations? Let us try to understand that. So the magnitudes of physical quantities may be added together or subtracted from one another only if they have the same dimensions. Please remember, only if they have the same dimensions. In other words, we can add or subtract similar physical quantities. Thus, velocity cannot be added to force. So the same concept which I explained you here. So the velocity cannot be added to force, or electric current cannot be separated from a thermodynamic temperature. Okay, the simple principle. What this principle is called? This principle is called as principle of homogeneity of dimensions in an equation. Okay, is extremely useful in checking the correctness of an equation. Okay, so let us try to consider this, and then let's move forward. So if the dimensions of all the terms are not same, the equation is wrong. Hence, if we derive an expression for the length of an object, regardless of the symbols appearing in the original mathematical relation, when all the individual dimensions are simplified, the remaining dimension must be that of length only. Okay, so what they're just trying to say, let's say we have some parameter k, l, m, t, -4, anything. These are not temperature, time, etc. Let's say everything is there, and we are just saying that the dimensions on the right hand side is L. Then everything which is written here should be cut forward, and finally the answer which is required, or finally with the thing which is left, should be in the dimensions of length only. That is the thing which is written. Okay. So similarly, if we derive an equation of speed, the dimension of both sides of the equation, that is LHS and RHS, when simplified, must be of length by time, LT inverse. Dimensions are customary used as preliminary test of the consistency of an equation when there is some doubt about the correctness of the equation. Okay. However, the dimensional consistency does not guarantee correct equation. Okay, so if let us say LHS is equal to RHS, every time it is not sure that the correct equation is correct only. Okay, sometimes some correction factor has to be added. Some other thing has to be plus, which also has the same dimensions, or minus has to be done of the same dimension, or multiplication has to be done by some factor, or division has to be done by same factor. Okay, so that the equation is correct. Dimensional consistency will tell you that it is the equation stands forth, but the correctness or accuracy of the cannot be told by dimensional consistency. Okay, so it is uncertain to the extent of dimensionless quantities or functions. The arguments the arguments of simple functions, this trigonometric, logarithmic, and exponential functions must be dimensionless. Okay, so these are functions are dimensionless. A pure number, that is ratio of similar physical quantities such as the angle such as the angle as the ratio length upon length, refractive index as a ratio. So these all concepts will be understood in 12th class, 11th class, etc. What is refractive index? Basically as a ratio, that is speed of light in vacuum upon speed of light in medium, etc. has no dimensions. And now we can test the dimensional consistency or homogeneity of the equation. So let us say we try to find out the homogeneity of this equation. Okay, that is x is equal to x naught plus v naught t plus half a t square. Okay, so to understand this, this is basically an equation which you will understand in the next chapter only. This is basically to find out the displacement occurred. For now, you can understand displacement as some path occurred. Okay, so what is the accurate description of displacement will be understood in the next chapter. Okay. So for the distance x traveled with a particle or body in the time t, which starts with distance x naught with a velocity v naught at time t equal to 0 and has an uniform acceleration along the direction of the motion. Okay, so let us say, so how to understand the concept here? The dimension of each term can be written as, so x equal to x naught plus v naught t plus half a t square. As you can see clearly, the dimension of left hand side was L only, and dimension of each and every quantity on RHS was L only. So it is quite evident you can add L plus L plus L. There is no harm in that. Hence, that it is dimensionally homogeneous. Okay. So as each term on the right hand side of this equation has the same dimension, namely that of length, which is same as the dimension of left hand side of the equation, hence this equation is dimensionally correct equation. Okay, so that was one of the conclusions. It may be noted that test of consistency of dimension tells us no more and no less than a test of consistency of units, but has the advantage that we need not commit ourselves to a particular choice of units, and we need not worry about convergence among multiples and submultiples of the unit. Okay, so it's basically a conversion or the consistency of units. It may be borne in mind that if an equation fails the consistency test, very important, please look over here. It may be borne in mind that if an equation fails the consistency test, it is proved wrong. So that means it is proved wrong. Even if the accuracy is correct, but it is wrong. If it is consistently wrong, then the equation is wrong. You have made a mistake somewhere. But if it is passes, it is not proved right, because then there may be some factors to be considered or something has to be added in order to make it more accurate or generally accurate enough. Okay. Thus, a dimensionally correct equation need not be actually an exact equation, but a dimensionally wrong, incorrect, but dimensionally wrong equation is always inconsistent, and it is wrong only. Okay, so if it is inconsistent, it is 100% wrong. But if it is consistent, there is a higher chance that the equation is right, but it depends upon the accuracy with which we are finding out the answer. Maybe there would be a k factor required there, or maybe there would be a factor of something with plus having the same dimension would be required. Okay, so that being said, let's look over to these examples and let's move forward. Okay, so the first example states that let us consider an equation that is half mv square is equal to mgh, where m is the mass of the body. So this is basically left hand side is your kinetic energy and right side is your potential energy. Okay, so where m is the mass of the body, v is its velocity, and g is the acceleration due to gravity, and h is the height. Check whether this equation is dimensionally correct. Okay, so if you need to check it, so it's nothing but, as you can see, it's half mv square equal to m GH. Okay, M has a mass of its M1, and this will give you L upon T squared. So this will be nothing but equal to M1 L2 T minus 2. Similarly, this will give you mass M1 G will be acceleration, that will give you L1 upon T squared, and height will give you again L1. So this will be again M1 L2, L1 into L into L will give you L2 and T minus 2. So as you can see, both sides are same, and hence this is dimensionally correct. Fine. So I explained you in front of you only. So this is basically, this is also energy, this is also energy. So this will be understood in subsequent classes. Fine. Let's go to the next example. The next example states that the SI unit of energy is joules. Okay, so joules is basically kg meter square s minus 2, h to the power minus 2, and that of velocity is meter per second. That of acceleration is meter per second square. Which of the formula for kinetic energy given below can you rule out on the basis of dimensional arguments? Okay, so what we just need to do, because kinetic energy is written, we know the unit on the left hand side. We just need to use our uh, knowledge about the things which are written on right hand side. If those things are same, then it is consistent. If it is not same, those are not consistent. Okay, so let's look over to the solution. So every correct formula or equation must have the same dimension on both sides of the equation, so we just need to check that. Okay, let us say for example we check for this. So it's nothing but it is M2 and it's L3T minus 3. Okay, similarly for MA, it is nothing but it's M1 and then it's L1 T minus 2. Okay, so therefore the dimensions of the quantity on the right hand side are M2 L3 T minus 3. So it's nothing but M2 L3 T minus 3. And kinetic energy is given, right? So kinetic energy, we have just answered it. It is M1 L2 T minus 2 here. Okay, and the dimensions on the right hand side are M2 L3 T minus 3. So this is basically this. For B it is this, for C it is this, and the quantity on the right hand side of E has no proper dimensions because it's energy multiplied by force here. So basically you cannot add a force and a velocity. So force and a energy. Since two quantities of different dimensions have been added, since the kinetic energy has a dimension M1 L2 T minus 2, M1 L2 T minus 2, formulas A, C, and E are ruled out. As you can see, E is directly ruled out. A is having different quantities, so this is also ruled out. And what else is ruled out? C is also ruled out because energy cannot be equal to this force. Note that dimensional argument cannot tell which of the two B or D is correct form. Okay, so we just need to understand. So this is one of the typical example. Really, if I explain you, this is the answer for kinetic energy. But as you can see, both B and D are having same dimensions. Hence, we need to justify our answer more. So the accuracy cannot be obtained as long as you know the correct equation. Dimensionally can tell you yes, the correct equation may be right, but equation may be wrong also. Okay. So basically this is correct answer for here, but actually kinetic energy is not 3/16 mv². Kinetic energy is half mv². Okay. Reducing relations among the physical quantities. So the method of dimensions can sometimes be used to reduce relation among the physical quantities. For this, we should know the dependence of the physical quantity on other quantities. Up to 3 physical quantities are linearly independent variables. Okay, so if you can understand why it is given as only up to 3 physical quantities, it would be very I think it will be beneficial. I think from me it would be very good if you understood this concept, why it is as 3 physical quantities only. Why not greater than that? So I will try to come to the situation after explaining this, and then we can look forward again. And consider it as a product type of the dependence. Let us take an example. So let us try to understand. So what basically we are trying to do, let us say we have something on the right hand side and we have something on the left hand side. By some experiments, let us say by some experiments, we got to know that kinetic energy is a function of mass and velocity, right? So basically what we can write, kinetic energy is nothing but equal to m to the power x, velocity to the power y, right? Now, as we know, if this equation is constant, the dimension of the left hand side will be equal to dimension on the right hand side. Just try to equate the constants, and that is the complete concept which is written here. That is reducing relations among the physical quantities. Well, the example has been done here. We will try to understand that example here once. Okay, so please look carefully. I will try to go slowly here. So consider a simple pendulum having a bob. Bob is basically a ball. You can understand this as a ball attached to a string that oscillates under the action of force of gravity. So only force of gravity is acting and it is oscillating. Suppose that the period of oscillation So this is how it is oscillating. It's going there, it's going here. So suppose that the period of oscillation of the simple pendulum depends on length L, mass M, and acceleration to gravity G. So they are saying that it is moving. So basically, the time it required for movement of from this location to this, and again moving work forward to here is basically time. They are saying that this time period T is a function of length L, mass M, and acceleration to gravity G. So derive the expression for its time period using method of dimension. So what is this method of dimension, you may ask? So the dependence of time period on the physical quantities can be written as like this, right? So maybe there would be some factor, multiplication factor, which we don't know right now, but length would be having some power, G would be having some power, and mass would be having some power, right? So if we try to write the dimensions of the left hand side and right hand side, we know that left hand side would be 1 second in a second only, because time is measured in second. So it would be L0, M0, T1. Length can be written as L1 to the power x. Gravity can be written as meter per second square. It's L1 T1 to the power y. And mass can be written as M1 power z. If you do some calculations here, you will get that it can be written as L to the power x plus 5, T to the power minus 2y, M to the power z. Now just try to equate these values here. So this can be equated. So we have three equations, three unknowns. So we have basically these equations. And we solve these equations, you will get the answer as equal to x is 1 by 2, y is minus 1 by 2, z is 0. Try to put this, you will get time period is nothing but k under root L upon G. Okay, so finally what we got is that there is no relation of mass. That is one of the things which you understood from this. But yes, we could not understand what is this factor of k. Okay, so when several other calculations were being done, we finally found out that this value was 2 pi. Okay, so but this value of k cannot be found out using your dimensional analysis. Okay, so note that the value of constant k cannot be obtained by the method of dimensions. Here it does not matter if some number multiplies the right side of this formula, but that does not affect its dimensions. Okay, so any factor can be multiplied here, but final accurate enough is k is equal to 2 pi. Okay, so actually k is 2 pi, so that k is equal to 2 pi under root L by G. So that is one of the factor, that is 2 pi under root L by G. This is also one of the things important in our class 11 and 12 syllabus, which you will understand in subsequent lectures or subsequent chapters. Okay. So therefore, dimensional analysis are very useful in reducing relations among the interdependent physical quantities. Please remember. Okay. So first of all, before analyzing the dimensional analysis, we would have done some experiments to find out what are the things on which our time period depends upon. Then only we can understand. Now, what if we couldn't have found out that it depends on G? Then we would have done just T is equal to K L to the power X into M to the power Z. Then this would have given wrong result, right? So that is why there is a necessity to find out or necessary to do the experiments also very clearly. So these are just based upon the researchers. So researchers basically adopt, or this is one of the way which researchers do to find out or reduce the relation between the physical quantities. Okay. So dimensional analysis is very useful in reducing relations among the interdependent physical quantities. However, dimensionless constants cannot be obtained by this method. Very, very important. So this is one of the example of dimensionless constants. Okay, so dimensionless constants cannot be obtained by this method. The method of dimensions can only test a dimensional validity, but not the exact relationship between physical quantities in any equation. Okay, so we cannot know the exact relation. We can just say that if the LHS is equal to RHS, that the dimension of LHS is equal to dimension of RHS. It does not distinguish between the physical quantities having the same dimension. Okay, so let us say if both are having same dimension, so it cannot distinguish there also. Then it's depending upon the knowledge and the experience of the worker or the person which is doing to segregate both of the physical quantities. Fine. So that being said, that is your end of your complete chapter of units and measurement. So that was all from you need to understand. But just one suggestion from my side: please try to solve questions based upon significant figures and dimension analysis, and that is the main crux of this units and measurements. Okay. So just the final course progress for you. We started with the introduction, in which we understood basically what is units and measurement, what is basically units, why we define such quantities. Then SI units, we understood why was there a need for SI units, so that researchers from one area can provide their experience or knowledge to other parts of the countries or other parts of the globe. Then we understood measurement of length basically. Okay. In SI units, we understood two things. One was fundamental quantities and one was derived quantities. There are seven fundamental quantities, and everything which is derived using fundamental quantities are called as derived quantities or derived units. Okay. Then in third subtopic, we understood measurement of length, in which we understood two different methods. For general purposes, we can use meter scale. Then for smaller distance, we can use vernier caliper. Then screw gauge can be used. Then spirometer can be used, etc. But for very large distances, we need to use a parallax method. One of the method is parallax method, and for very small distances also we understood some of the concepts such as tunneling microscopy, etc. The next thing we understood measurement of mass, in which we also understood very small masses. We cannot use kgs. We use one atomic mass unit. Then we understood measurement of time about cesium clock, atomic clock, etc. is being dealt here. Then in accuracy, precision of measurement and error in measurement, we understood what is basically error, why does uncertainty arises, what are the two types of uncertainty, random errors, what is basically the set of errors, etc. Then we also understood three different quantities, that is absolute error, relative error, percentage error, etc. Here we also understood combination of errors in this concept. Then we went on to significant figures. Okay, then we understood all the rules beside significant figures, how to multiply, add, divide, etc., and finally obtain the results. One of the rule which say that we generally find the answers up to all the decimal places for intermediate steps, and then finally do the significant figures concept in the last concept only. Okay. Then last three concepts were based upon dimension analysis only. So we understood basically what is the dimension of physical quantity, what is basically dimensional formula, etc., what is dimensional equation, and one of the application of dimension analysis was utilized here. As in which understood about using a basic example, as in we first of all experiments were being done and it was being found out that the time period is directly proportional as a relation between, let's say, mass, length, and time, length and gravity. Then using dimensional consistency, that is on the left hand side, the dimensions are same as right hand side. We finally found out that time period is nothing but equal to k times under root L upon g. It is not. It does not depend upon mass. And then finally, we found out that that k value cannot be using dimension analysis. Some other experiment has to be done to find out this value. Okay. So that is the end. That thank you for listening from my side for your units and measurement. So thank you so much.